This next problem is a typical angled launch problem from ground. The Seneca Golden Eagles are about to start the game and kick off to their opponent. The kicker kicks the football with an initial speed of 24 meters per second at an angle of 40 degrees above horizontal. Ignoring air resistance, find out how A, how high the football rises, B, how far it travels before it hits the ground, C, the time in the air, and D, how fast it is moving when it hits the ground. Alright, so just like before, the first thing we want to do is actually draw a diagram. Okay, so we have football being kicked off at 40 degrees above the horizontal at 24 meters per second. So let's go ahead and plug this into our chart. We know that, wait a second, I can't just go and plug that in, can I? Because this actually kicked off at an angle. Well, there is one thing I can do is 0 meters per second squared and negative 9.8 meters per second squared for the acceleration. But to really break this down into the components, I need to actually start with this velocity vector, which this is the resultant vector. I need to break that down into its horizontal and vertical components. This is the first thing I need to do. So again, remember that if this is my velocity vector v, I actually have a horizontal component here, v sub x, and I have a vertical component, v sub y. And to create this triangle, this right triangle, I move this over to here such that here is my v sub y, and that's what creates this right triangle. My angle is right here. So if I look at the relationships here, I know that the sine of theta is equal to v sub y over the hypotenuse, which is v. But I'm trying to solve for v sub y. So v sub y is actually the actual resultant velocity vector times the sine of theta. And then to find the horizontal component, I know that the cosine of theta is equal to v sub x divided by v, such that v sub x is going to equal to v times the cosine of theta. So these equations right here, anytime you have to break up an initial velocity vector, or to be honest with you, any velocity vector along this entire path, this is going to be the relationship here. Okay? So let's go ahead and solve for these vertical components. Again, this is the initial vertical and horizontal velocities. So v sub y initial is going to be the 24 times the sine of 40 degrees, which is equal to 15.427 meters per second. And the initial horizontal initial velocity, that is equal to the 24 times the cosine of theta. V sub x initial is going to be equal to 18.385 meters per second. Okay, so I could take these and then plug them back into here. Again, I found my horizontal and vertical components of my overall velocity. Remember, because this velocity vector is going off in two different directions and I have two different accelerations occurring in different directions, I need to treat them separately and analyze everything in the vertical and everything in the horizontal separately using the uniformly accelerated motion equations. So my initial horizontal is 18.385 meters per second and 18.385 meters per second. Again, zero acceleration. Once I find my horizontal, I know that's consistent all the way through. My vertical is 15.427. All right. So the first part says, well, how high is the football? How high does it rise? Well, that means where is its maximum height or the maximum altitude? And we know at this particular point that the vertical velocity is equal to 0. Okay, so this is where you have to apply your conceptual understanding of an object in projectile motion. It ties back to free fall and the vertical, okay? So what we need to do is solve for the displacement with the understanding that my final velocity in the vertical is going to be 0. Okay, again, since we know that the vertical velocity is 0 at its maximum, to find this total altitude, the maximum height of the football, we're going to use this equation, v squared equals v initial velocity squared plus 2 times the displacement in the vertical. So our final velocity to get to the top is going to be 0 equals plugging in 15.427 squared is my initial vertical velocity plus 2 times the acceleration due to gravity, negative 9.8 meters per second squared, times the displacement in the y. Moving these over, subtracting this over, and then dividing by the 2 and the negative 9.8 will give me a vertical displacement of 12.14 meters. So that's how high it will travel when it is actually at the top. So that's the first part of A. Now B actually says, well, how far does it travel before it hits the ground? So we're no longer analyzing this point, okay? We're actually trying to analyze all the way down to here. Now we have two different things that we could do. We could change our final velocity. What is our final velocity in the vertical right here? Well, conceptually we understand that if it's at the same vertical plane, that if I have an initial vertical velocity of 15.427 meters per second, that means right here I'm going to have negative 15. At the same plane here, I'm going to have, if I have initially positive 15.427 meters per second, that means at the same plane, I know that the vertical velocity at this point right before it hits the ground is going to be negative 15.427 meters per second. So I can plug that in over here and solve for the time, which we'll go ahead and do that. You could also, though, knowing that this is half of the flight, so the time that it takes to get to here, if I use this displacement and a final velocity of 0, I could solve for the time to get to here and just double that time, because I know that everything to get to here is the same as it is from here down to the ground at the same height. Either way will get you the same time, but let's just go ahead and use our understanding that the final velocity vertical vector right before it hits the ground is going to be the same magnitude but opposite direction as we started with. So we'll use that to solve for the total time in the air. Okay, so we're using that first equation. The vertical velocity final is equal to the initial vertical velocity plus the acceleration in the y times time. Plugging in, negative 15.427 is equal to 15.427 plus the negative 9.8 t. All right, doing some algebra and solving for t, we get the time for the full flight of the ball is 3.14 seconds. Now, that is actually c. But why did I solve for time? I said I needed to actually solve for the displacement of how far it is. But remember that our horizontal is really a function of the range that it is going to travel. So from here all the way over is our range, is based off of the velocity in the x times time. Well, I couldn't get time from this, so I actually had to solve for the time first in order to get to the displacement in the vertical direction. Excuse me, the displacement in the horizontal or the range. So since we have the time, we can write that in here. 3.14, 3.14. We'll go ahead and plug in and solve for here. Okay, again, this is just a breakdown of this equation. But since the acceleration in the horizontal is always 0, we end up with just this equation because it's constant velocity. Plugging in, we have our horizontal velocity times time will give us 57.8 meters is the range, how far this football actually goes. Well, the last part asks for the final speed. How fast is the football moving? So we're looking for the magnitude of this final velocity here right as it hits the ground. This is where you could go through and solve and work out the math, but really conceptually is all you need to do is understand what we already talked about several times now about projectile motion. If the vertical velocity we've already discussed is negative 15.427, we are at the same plane that launched from the ground. I know that my horizontal velocity is never changing, so I have the 18.385 meters per second in the horizontal. If I have the same horizontal and same vertical, just in the opposite direction, well, this resultant velocity vector is going to be the same as it was here, which was 24 meters per second. So how fast is it moving? Well, the final velocity here is going to be 24 meters per second. And that's just conceptually understanding. I could go through and actually do the Pythagorean theorem to solve for it, but it's going to be the exact opposite of what we did to break it up into the components up here when we first started the problem. In fact, the problem's only asking for the speed, which is 24 meters per second. That's how fast it hits the ground with, the same speed that it was kicked with. But we could also take this a little bit further if we wanted to and know that this angle here, it was launched at 40 degrees above the horizontal. Well, the actual angle is going to be negative 40 degrees, or 40 degrees below the horizontal. So actual speed as it hits the ground, adding an angle to it would give it the velocity. This problem only asks for speed, but we know this is where the concepts of what's going on with projectile motion help us to break down and analyze this problem. So the key for this problem and any other one that's an initial angled launch, and that's an angled launch from elevated or actually from the ground, when you're given the initial speed and angle, the first thing you need to do is break it up into the horizontal and vertical components and plug it in. So this is always going to be that first step. If you're given information that's not in either the horizontal or vertical components, break it down and start to work through the chart, applying it to each side.